Okay, this video is going to be a very quick epilogue to section 5.2 from Math 311, a course of linear algebra at Western Illinois University. I failed to include this in both the video and the notes, but it's very, very important, and it has to do with the dimension of a subspace and its dual. And it says that a very important fact, it should be a theorem, but I'll just leave it as a fact, that if W is a subspace of Rn, then the dimension of W plus the dimension of W perp is equal to n. Okay. All right. And that's kind of what you could sort of see. For example, in R3, when we had a plane, we found out that its orthogonal complement was a line, and the plane is two-dimensional, the line is one-dimensional, and 1 plus 2 is 3. Okay, and that holds for any subspace. So why is that here? Well, so here's our proof of this important fact. And it goes. What we're going to do again is we're going to cheat a little bit and use the fact that every subspace has its own orthogonal basis. Okay, which we will prove in section 5.3. So we're going to let W1 through WK be an orthogonal subspace, or orthogonal basis of W, and we're going to let U1 through UL be an orthogonal basis of W perp, because W perp is a subspace, and so it'll have an orthogonal basis as well. Okay. Again, we can prove this. We will show why we can do this later. Okay, and by that I mean next lesson. All right. So what we're just going to do is we're going to combine these vectors and into one big set. So I'm going to let B be W1 through WK, and U1 through UL. Okay, and we're going to claim that this is a basis for Rn. Okay, so this is a basis for Rn. Okay, so the question is why? Well, first of all, we can see that it will certainly be a spanning set, right? Because we know that any element, the orthogonal decomposition theorem says that any vector in Rn can be written as a linear combination of, it can be written as a sum of something in W plus something in W perp. Okay, and anything in W is going to be a linear combination of these vectors, and anything in W perp is going to be a linear combination of these vectors, right? Okay, so by the orthogonal decomposition theorem, any vector in Rn is in the form, or is of the form, W plus W perp, okay, and this is in the span of the W's, and this is in the span of the U's, the UI's, right? So thus, so A is a spanning set for Rn. now the only thing else we have to see is why is it linearly independent? Well, it's linearly independent because we're going to show that this is an orthogonal set. Okay, and all orthogonal sets are linearly independent. We have that all these W's are orthogonal to themselves, and all the U's are orthogonal to themselves, because this is an orthogonal basis. And since each little w is in big W, and each U is in W perp, each little w is going to be orthogonal to each little u. Okay, so that means that this is going to be an orthogonal set. So wi dot wj equals 0 for all I not equal to j. Similarly, ui dot uj equals 0 for all I not equal to j. And we know that wi dot uj is equal to 0 for all for all ij. Okay, so that means that B is orthogonal, which means that B is linearly independent. Okay, which means that B is linearly independent, and B is a spanning set, so that means that B is a basis of Rn. Okay, so that means that n must be equal to, n is the dimension of Rn, so that means that what's the size of B? It's going to be k plus L, and k is the dimension of W, and L is the dimension of W perp. Okay, so that proves that very important theorem, and I thank you for your patience.